Eccentric loading. This is my third and last part of today's online lecture. I've already explained you about eccentric loading. The definition of eccentric loading is the line of action of load does not pass through the centroid of rivet system and all rivets not will loaded. The joint will be called eccentric loading. I have already explained in the previous figure, end of the lecture, what is eccentric loading. In case of eccentric loading, there are two types of shear: direct shear and or primary shear and secondary shear. In the first previous examples, the shear was primary shear because there were only a shear due to shear force. In case of secondary shear, there can be load. For example, in this case, the rotation that this load has to be resisted by this external and opposite moment. And this moment, the resistive moment at G will be resisted by moment by force at each bolt or rivet. Each of these forces will create a moment about this point. And at the end, these resistive forces, this moment, reaction moment will cause forces in each of the moment. Also, this P will exert 1/4 of load on each of the bolt and there will be a resistance of P by 4 on each bolt. This P by 4 will be primary shear and these forces due to bending moment is secondary shear. And all these reaction force and moment will act at point G of rivet system. For example, if you have 2, 3, 4, 5, 10 or say 50 rivets, there will be G. And how we calculate the G? It can simply calculated by A1, X1, A2, X2 area of rivet 1 into distance of rivet 1 from, for example, take point O. From this O, we have distance of all the rivets in X direction and area. If let's say we have same diameter of all the bolts, in that case A1, A2, A3, A5 all are the same. Similarly, A1, A2 are same. It will cancel out, so we are only left with the distance parameter x1 plus x2 plus x3 plus x4 divided by number of bolts will give you us x bar or center of point position of center of gravity at centroid from this O. Similarly, for y bar, we have same equation. If a bolts are of same area, then this a divided by a can be cancelled out. So we are only left with yi, distance of each rivet divided by number of rivets or bolts. So this is the method to calculate G. Once you calculate G, we know that all the force, all the moment, bending moment acts at this point G. For any rivet system, there is a point G. There is a bending moment. There is a due to this force, there is a shear force and bending moment. This shear force and bending moment acts at the centroid, and similarly acts at centroid. From this, primary shear is V1. Simply, we have V1 divided by number of rivets give us primary shear force on each rivet or each bolt. For secondary moment, we have an equation. Yeah, this one. If let's say there is a moment M1 resisted by this bolt system, 4 bolt and a centroid at O. If moment 1 is resisted by this system, there is will be a portion of moment resisted by bolt at A, portion will be resisted bolt at B, similarly bolt at C and D. So total sum of moment will be moment resisted by A, moment resisted by B, plus moment plus number of all the moments resisted by all the bolts in the system. Also, we know from this trigonometry the further the distance. For example, if we take a rivet at distance at this point, the force applied by resisted by that for to resist that moment will be equal to this force. So this just we have a similar triangle here. So if we have a distance, half distance from here, the force on that will be 1/2 from that. If it is Ra by 2, then the force will be Fa by 2. So we have a trigonometric relationship between forces and distances. Fa, secondary shear force by rivet A divided by radius distance from perpendicular distance from O. This ratio is same for all. This ratios remain same for all the cases. Now we have two equations, one this and two this. From this equation, we can calculate force resisted by each bolt. Also, we have once we know the F double prime. This is secondary shear force divided by area will give us secondary shear stress. And similarly, for primary shear stress, pi top prime equal to 4 F prime by pi d square. It was for primary shear. We have this equation, and similarly we have this equation. Using these two equations, we can calculate, for example, Fa double prime is equal to this. Similarly, we know that Fb double prime will become equal to Rb by Ra into Fa. Substituting this value, that equation will be only as a function of Fa, ratio of Rb and Ra, ratio of Rc and Ra. At the end, we take Fa common, Fa double prime common, and the final value will be can be calculated by ratios of Ra, Rb, Rc, and Rn. N is the number for which we are calculating F. For example, for Fa is equal to R, it will become Ra, and it will come, we will calculating Fa double prime. So by using this equation, we can calculate secondary shear force on each bolt. For most of the cases, bolts are made of same material. Pi by d is same for all the bolts. So if this is the same, then the bolt which is for which F, the magnitude of F and double prime and F prime is maximum, will be failing first. For example, we have primary force acting downwards, say, and similarly we have secondary force F and double prime and F and prime. We have two forces acting on one bolt. So the resultant can be calculated simply by calculating F n prime square plus F n double prime square. This will give us resultant force on one specific bolt. We can calculate force on each bolt. As the cross-section area of all the bolts in a system is usually same, so the bolt which is resisting the maximum amount of load, we have to design only that bolt. If we select a suitable dia for that specific bolt, we can use same bolt for all the other holes and the system will be safe. Applying this whole theory on this simpler example, in this example, they have given us a load of 16 kilonewton applied at distance 300 from the edge, and the centroid is, because this is a square distribution, centroid can be calculated at exactly center in x direction and exactly at the center in y direction. So this center, if you want, you can use the equation for x bar and y bar. I have just shown you in slide number 20 or 21 or 22. Uh, Once we have value of this, we can just calculate primary shear is F divided by 4 because we have 4 bolts. So primary shear will become 16 by 4 equal to F prime come equal to 16 by 4, or we don't have any picture here, so 16 by 4 or 4 kilonewton. For secondary shear, F multiplied by moment arm, which is equal to 300 plus 50 plus 75, or 425 into 16, will give us a moment. This moment is equal to 16 multiplied by 300 plus 50 plus 75, and the magnitude of this moment is equal to, let me check from my paper, this moment is 6.8 kilonewton meter. 6.8 kilonewton meter. We have magnitude of this moment, and using previous equation we can calculate the magnitude of fa double prime, fb double prime, fc double prime, and fd double prime, and the direction. Because it is a resistive moment, the moment acting on and the resistive force will be like this on each bolt, but the force acting on the bolt will be in the opposite direction, as I have already explained when I was explaining direction of forces. So this is fc, for example, this is fa double prime, this is fb double prime, this is fc double prime, and this is fd double prime. As for all the cases, r is same, so the magnitude of fa double prime, b double prime, fc double prime, and fd double prime becomes the same. So the magnitude of forces of all the four secondary shear will be 17.7 kilonewton. So f double prime is equal to 17.7 kilonewton for all the four bolts. But if you see the direction, these two are in opposite direction, this and this, f prime and f double prime. But in case of a and b, they are two are in similar direction, so the final magnitude is higher in this case, in case of a and b, and this magnitude is lesser in case of c and d. So if you calculate magnitude of 17.7 and 4, and after using angle, because we have angle as well, so using the values, using trigonometry, we can just check what is the magnitude of f this resultant magnitude of force acting on each bolt. For A and B, for bolt A and B, the final resultant magnitude is 20.97. This final resultant is 20.97, or say 21 kilonewton. And for these two, it is 14.8. So more forces are acting on bolt B and A as compared to C and D. So we have to design bolt with reference to 21 kilonewton of force. So this is a part 1, the resultant load on each bolt. In the part 2, they asked us to calculate the maximum shear stress in each bolt. And for maximum shear stress for bolt will be at this cross section. In the book, if you see, they have calculated a lot of things. For example, what they have done in the book. For example, this is a total length of bolt. This is bolt head. From there, they calculated thickness 1, 15, thickness 2, 10. So we have thickness of material 1, thickness of material 2. Then we have one nut. Then we have 2 extra threads. So it will give us total length of bolt. Once we have length of bolt, from the chart we can calculate what is the length of threaded portion, that we can use from table 8.7. Once we have length of threaded portion, we have the grip, which is equal to 15 plus 10, 25 mm is the grip. So L is 25 mm. We have length of threaded portion. So from this we can calculate length of unthreaded portion. Once we have this length, which is equal to length of bolt, once we have length of bolt minus length of threaded portion will give us length of unthreaded portion. And if this LD is more than 15 mm, it means that thread starts from here. And if this LD is less than 15 mm, thread starts from here. So it is only to check either at this cross section we have a threaded portion of the bolt or unthreaded portion of the bolt. If at this point we have a solid bar or unthreaded portion of the bolt, Then to calculate this area, we have to use 16 mm. So the area, if this is solid portion, then the area will be pi by 14, 16 square. And if the area at this point is unthreaded, is threaded, then we have to use value of AR from table 8.1. AR, sorry. So in this portion, they calculated the value which comes out to be length of unthreaded portion is 8 mm. In other words, if this is the first plate, the shearing will be done here. This is 15 mm and length of unthreaded portion is only 8 mm. It means that thread starts from here. In other words, at this point there we have a threaded section. So we have to use AR from table, and force divided by AR will give us shear stress. And from that shear stress we can just compare that shear stress, uh, that will give us shear stress on each bolt. Sorry, this will be a shear stress. For bearing stress, for same for same figure, for bearing stress, what is the maximum bearing stress? This is the area. This dia is the area, and the acting force divided by this area, which is equal to thick height, which is 15 mm, into diameter, which is equal to 16. This is equal to bearing stress of bolt or bearing stress of plate, both cases. Similarly, for this plate as well, we have bearing stress, and it is equal to 10 into 16 is the area. Force divided by this area gives us bearing stress in this plate as well. In the last part, we need to calculate critical bending stress, and for this I will explain this thing in the problem, and because this is the example and you can study this in detail in the book, so I will just explain this thing with the problem. In this problem, this is the last problem of the chapter, and is after that the chapter is ended. Because this is online lecture, that's why I have explained a lot of detail all the things. Otherwise, for the class it has had to be over in 2 or 3 hours. For this problem, they have given us bolts. What bolt they are used? They have given us thickness of plate. Force is applied here. So due to that force, there is a equal and opposite. There is equal and opposite force upward in this direction. This is the upward force, 12 kilonewton. Because we have 3 bolts, this 12 kilonewton is divided. So we have applied load on the not resistive applied load. So on each bolt we have downward 4 kilonewton force on each bolt, because it is not, we are not calculating reaction, we are calculating only action on the bolt. Similarly, this for this 12 kilonewton multiplied by 200 gives us a bending moment resistive, bending moment not resistive, a bending moment in the same, sorry, in the same direction, bending moment, not this one, this bending moment of 12 into 200 or 2.4 kilonewton meter. 2.4 kilonewton meter. We have bending moment, and from the equation that I already explained, because in this case as well, x bar is for all the holes are in line, so x bar is same and y bar is also same. So this point is the or centroid of this whole system. It is not difficult to calculate, but you, if you want, you can use the equation of x bar and y bar to calculate x bar and y bar. Then we have equation for example, to calculate F A double prime, we have the equation of ratios of R's. So it is M R A divided by R A square plus R B square plus R C square. This is whole, just to mention, this is whole A, this is whole B, and this is whole C. A and C are at same distance and B is at the centroid, so this term is equal to 0. So by solving this equation, we get FA double prime equal to FC double prime, which is equal to 37.5 Newton, and FB double prime is equal to 0. So if we calculate resultant, because for all values resultant is, for example, for this case resultant is in this direction, for this case resultant is in this direction, and our FA was downward, here as well FA was downward. So calculating the resultant, it will give us FA. Simply you need to calculate F for A, FA prime plus whole square plus FA double prime square under root, similarly for C and similarly for B. So we get FA resultant becomes equal to 37.7, and similarly FC as well, and FB is equal to 4 kilonewton. So it's kilonewton. It is also kilonewton. So we have a maximum force acting on a single bolt is 37.7 kilonewton, and we have to design a bolt with which can say securely support this much amount of force. In the next part, they ask find the factor of safety of following failure modes: shear of bolt, bearing of bolt, bearing in the bracket. So I will just clear this. So I have cleared the screen. For 5.8 ISO 5.8 bolt, you can just go to the table and check the value of SP for this bolt. Let me write here. SP for 5.8 bolt is equal to 380 MPa, and similarly SY is for 20 MPa. Or similarly for material which is given 1020 hot rolled steel, you can check SY from table A20 in the appendix. It comes out to be 220 MPa. So we have the values of strengths. What is the area of bolt? We have M12 12 millimeter bolt, so we can calculate area of bolt pi by 4 12 square, which gives us a value 113 mm square. This is the area of bolt. Also, because we have yield strength for shear, we can check what is the shear yield strength of bolt. It is 0.577 into 420, that will be the strength. Shear stress on each bolt, tau, and what was the maximum load? 37.7 kilonewton or 37,700 Newton divided by this area 113 millimeter square, and from that we can calculate the stress on the single bolt. Maximum stress on bolt is 333 MPa. And for us to calculate factor of safety, we have strength which is equal to 0.577, because we need to calculate shear strength multiplied by 420 normal yielding divided by this 333 will give us maximum factor of safety against shear in the bolts. Similarly, if we need to calculate factor of safety against bearing of load, bearing of bolt, for bearing we have the area thickness, dia into thickness of this plate. So all the things are same, only area will be changed, which is instead of 113, we will be using an area of, what is the diameter? 12 mm. And what is the thickness? 8 mm thickness. So this will be the area that we'll be using for bearing stress. So this will be the AB, 96 mm square. And if you need to calculate again factor of safety, that will be equal to, again, bearing stress is not shear, so we do not need to multiply 0.507. So in that case, n is equal to 420 divided by stress, which is equal to force divided by area. And what is the force? 37.7 divided by 96 mm square. This is the bearing strength, or this is the sigma b. This is yielding divided by sigma bearing will give us factor of safety, and it comes out to be 1.07, and the previous part 0.728. Bearing in member, for member as well, sigma b will be same. Sigma b will be same for members, but only strength will be different. So for member, n will be for this bearing of bracket. So only thing is different for bracket is material. So nb for bracket will be equal to 210 divided by this sigma b, and this value is exactly half, half of 1.0.534. So we are only left with bending of bracket. That is a little bit tricky, but we need to calculate this as well. Initially, I need to, okay, I need a wide screen, so just start from here. For bending in plate, for example, bending in plate, where the bending is done. For example, bending is done here. This cross section, this thick cross section. This will be in bending because this is a load applied here and load is applied here. So it will be bent. It will be bent like this. Due to bending, the final shape will become like this. Initial shape is this, and due to bending, final shape will be like this, and there will be stresses in this direction. So we are required to calculate bending stresses. So cross section at the bolts, at the point of bolt will be, so cross section is like this. There are three holes, one for bolt A, one for bolt B, and one for bolt. There are three holes, so the total area is this. The moment is known, bending moment, the distance of force multiplied by the force multiplied by moment arm was equal to that I we are already calculated 2400, 2.4 kilonewton meter. That was the bending moment already calculated. The value is, we need to calculate I. Only tricky thing is to calculate I. What is I? I is the second moment of area of this section. For I, we have the equation for summation of H by 12 plus E square. Here we have one solid rectangle, now big solid rectangle minus this, minus this, minus this. If we take a big area, we can say that for i's will be equal to bh cube by 12 of the bigger area, for which b is equal to the thickness. I think that was 5 or ah b was 8 and h is equal to 36 plus 36 plus 64, that is h. So for this we have I is equal to, for this thick section like this, there is slot for one hole, slot for second hole, and slot for third hole. So we have, for the bigger area, we have B, which is equal to 8 into H, 64 plus 36 plus 36. Uh, 60 plus 4 plus 36 is 100 and 136 H cube by 12 minus, because all the other things are, these are loss of material, plus B, which is again 8 into dia of hole is 12, I think, yes, 12 cube by 12, this is for hole B, minus 2 times, because hole A and C are at same distance, so 8 into 12 cube by 12 plus 8 into 12 into D square, which is equal to uh, 632. This is the value of I. Value of I comes out to be 1.48 into 10 power 6 mm 4. We have I, we know magnitude of M 2400, we know C, where will I will maximum at this point 32, or at this point compression or tension. So sigma is equal to 2400 into 32 plus 36 gives us 68, 68 mm, divided by I, and we have all the values. Substituting a value give us 110 MPa of bending stress, and we have to compare this value, because this is bending stress in beam. We have to check it with the yielding of beam, yield strength of beam, and that was equal to, factor of safety is equal to 210 divided by 110, which gives us 1.91. So this is the yielding bending of bracket, factor of safety against bending of bracket. So that's all for the chapter of bolts and fasteners. So in the next, during the, before the next Sunday, I will submit another video for not this chapter, but I hope that it will be for the chapter of welding. Best of luck, and during the week also we will decide someday for question answer session, and I will be online for answer any queries that you will have for these three parts of the lecture. Thank you and best of luck for the lecture.